Contrary to popular belief, warmth doesn't guarantee comfort during sleep. Your brain's thermoregulation centers, the preoptic area of the hypothalamus, actively lower your core temperature by 1–2 degrees Celsius overnight. This cooling starts 60–90 minutes before sleep onset. The process isn't passive, but an orchestrated effort to optimize sleep stages. Melatonin, released by the pineal gland, drops your body temperature and signals your circadian clock, your internal timekeeper. At a cellular level, neurons alter ion channel activities, contributing to this temperature shift. This transformation primes the brain for the deeper, more restorative phases of sleep, crucial for cognitive function and memory consolidation. Your body's temperature drops as sleep progresses, yet the perfect ambient bedroom temperature remains a myth. The National Sleep Foundation suggests 15–19 degrees Celsius, 60–67 degrees Fahrenheit, as ideal. This range aligns with the body's natural cooling process. Thermoregulation during sleep involves vasodilation. Blood vessels widen to release heat. As vessels in your extremities expand, core temperature decreases. Counterintuitively, cooler environments aid this mechanism. However, individual comfort varies due to differences in skin blood flow and metabolic rates. The hypothalamus monitors these changes, adjusting to maintain equilibrium. This delicate balance underscores the importance of an ambient temperature that supports thermoregulatory function. While cozy blankets seem appealing, they can hinder your brain's thermoregulatory efforts. Excess warmth disrupts slow-wave sleep, the deepest phase where glymphatic waste clearance maximizes. During sleep, interstitial spaces expand by up to 60%, facilitating cerebrospinal fluid flow to clear metabolic waste. The glymphatic system, first characterized in 2012, operates more efficiently in cooler temperatures, enhancing brain detoxification. Cerebral blood flow decreases while arterial pulsations drive this purifying rhythm. Overheating can restrict this process, compromising cognitive restoration. Understanding this mechanism helps dispel the myth that warmer means better for sleep. Temperature fluctuations in your environment profoundly impact sleep architecture. A study by the University of South Australia in 2018 found that cooler room temperatures increased the occurrence of REM sleep by 30%. REM sleep is vital for emotional regulation and memory processing. During this stage, brain activity mimics wakefulness, but muscle tone decreases. Neurons communicate more rapidly, utilizing neurotransmitters like acetylcholine, which are sensitive to temperature changes. The thalamus regulates these shifts, ensuring efficiency in synaptic transmission. Striking the right balance in your bedroom's climate can thus significantly influence REM sleep dynamics. When it comes to sleep, the myth of one-size-fits-all temperature is misleading. Gender, age, and even genetic factors influence your thermal comfort zone. Older adults, for example, have reduced thermoregulatory capacity, requiring slightly warmer conditions. A study published in Nature in 2021 showed that individual variance in thermosensitivity is tied to TRPV1 receptor expression. These receptors in sensory neurons detect changes in environmental temperature. The brain integrates this sensory input to fine-tune homeostasis. Understanding these nuances can help tailor your sleep environment to support optimal neural and bodily functions, debunking the myth of a universal sleep temperature. Adenosine, a byproduct of ATP metabolism, accumulates in your brain as you stay awake, promoting sleep pressure. This neuromodulators build up peaks just before sleep onset, binding to A1 receptors in the basal forebrain to inhibit excitatory neurotransmission. The process is temperature-sensitive. Cooler environments enhance adenosine's sleep-promoting effects. A study in 2019 by Harvard Medical School revealed that a 2-degree reduction in room temperature accelerates adenosine clearance post-sleep, optimizing wakefulness. The glymphatic system aids this clearance, and its efficiency is temperature-dependent. Thus, cooler bedroom conditions not only support adenosine kinetics, but also bolster restorative sleep phases. The glymphatic system, a macroscopic waste clearance system discovered in 2012, is vital during deep sleep. It functions optimally at cooler temperatures, where interstitial fluid channels expand significantly. Astrocytes play a key role by expressing aquaporin-4 channels, facilitating cerebrospinal fluid influx. This fluid clears metabolic waste, including amyloid beta, a protein linked to Alzheimer's disease. Research by the University of Rochester Medical Center found a 40% increase in glymphatic activity at lower ambient temperatures. This underscores the importance of a cooler sleep environment, as thermoregulation significantly impacts astrocyte function and glymphatic efficiency. Circadian oscillator genes, like clock and BMAL1, regulate your biological clock and are influenced by temperature. These genes modulate the expression of purr and cry proteins, which in turn affect sleep-wake cycles. Ambient temperature fluctuations alter the activity of these genes, impacting the timing of melatonin release. Lower temperatures synchronize circadian rhythms, improving sleep onset latency and duration. A 2020 study by Stanford University demonstrated that cooling the sleep environment by 2 degrees Celsius shortened sleep onset by 20%. This illustrates the intricate relationship between temperature, gene expression, and circadian regulation. The cortisol awakening response, crucial for morning alertness, is also influenced by sleep temperature. Cortisol levels naturally rise in the early morning, promoting wakefulness. However, cooler sleep environments stabilize cortisol secretion by enhancing the feedback loop between the hypothalamus and adrenal glands. This feedback involves the hypothalamic pituitary adrenal (HPA) axis, which regulates cortisol production. A 2017 study in the Journal of Clinical Endocrinology and Metabolism found that individuals sleeping in cooler rooms had a 15% more stable cortisol profile. This reduced morning grogginess, linking optimal room temperature to effective cortisol regulation. REM stage memory consolidation relies on orexin-hypocretin signaling, a neuropeptide system sensitive to temperature changes. Orexin neurons in the lateral hypothalamus regulate wakefulness and are modulated by temperature. Cooler environments enhance orexin receptor signaling, facilitating transitions between sleep stages. This enhances REM sleep, where synaptic plasticity and memory consolidation occur. A 2021 study from the University of Tokyo found that a cooler room led to a 25% increase in orexin activity during REM sleep. This supports the role of ambient temperature in optimizing memory-related neural processes. Chronic exposure to improper sleep temperatures can have long-term effects on your brain and body. Sleep debt, resulting from consistently poor sleep, disrupts the prefrontal cortex, impairing decision-making and attention. A study conducted by the University of California, Berkeley, in 2018 highlighted that individuals experiencing chronic sleep debt had a 12% decline in cognitive performance. Acute deprivation, such as a single night of insufficient sleep, similarly disrupts glucose metabolism and increases stress response. This is regulated by the hypothalamus, which becomes less efficient at moderating cortisol levels with sleep loss. Temperature plays a critical role, as cooler conditions can mitigate these adverse effects. Sleep tracking apps often suggest personalized sleep environments, but oversimplify the complexity of ideal sleep conditions. While they monitor movements or heart rate, they fail to capture polysomnography data, which tracks brain waves and eye movements. Polysomnography, the gold standard in sleep studies, reveals that room temperature significantly impacts sleep architecture, including REM and non-REM cycles. A 2022 review from the Sleep Research Society emphasized that cooler temperatures enhance sleep efficiency by up to 10%. This showcases the inadequacy of apps in assessing optimal sleep conditions, as they lack comprehensive physiological measurement. The wellness industry often promotes sleep accessories like heated blankets, but research tells a different story. Excessive warmth disrupts sleep continuity, particularly affecting the slow-wave sleep stage. A 2019 study in the American Journal of Physiology highlighted that individuals using heated bedding had a 15% decrease in slow-wave sleep. This stage is crucial for physical restoration and growth hormone secretion. The hypothalamus, which regulates growth hormone via the pituitary gland, responds poorly to elevated temperatures. This misalignment between industry advice and peer-reviewed literature underscores the need for evidence-based sleep environment recommendations. Extreme temperatures, whether too hot or too cold, can lead to sleep disturbances and physiological stress. Overheating increases metabolic rate, leading to frequent awakenings, while excessive cold can activate thermogenic pathways, causing shivering. Both extremes activate the sympathetic nervous system, releasing norepinephrine and increasing heart rate. A 2020 study from the University of Zurich found that heart rate variability, a stress indicator, decreased by 18% in unfavorable sleep temperatures. This physiological stress can exacerbate sleep disorders, including insomnia and sleep apnea, illustrating the importance of maintaining a balanced sleep environment. Reframing our understanding of sleep temperature, a 2021 meta-analysis by the University of Copenhagen revealed that just a 1 degree Celsius change can shift sleep efficiency by 5%. This study synthesizes data from over 5,000 participants, illustrating the nuanced role temperature plays in sleep quality. Sleep efficiency, defined as the ratio of time asleep to time in bed, is crucial for restorative sleep. This finding challenges simplistic advice and underscores the need for personalized temperature settings in bedrooms. By examining the interplay between temperature and sleep, this research offers a precise perspective on optimizing sleep environments.